So we're going to go through your intro to inference, the AAA battery example. Before we even start chapter 7, we're going to go through that. So I've created a PDF, but you should follow this. I've created a PowerPoint slides that go along with that PDF handout. Okay, so assume that you are a statistician for a large battery manufacturer. The company has developed and manufactured a new AAA battery that the engineers say will last 17 hours with a standard deviation of 0.8 hours. The batteries produced during the first day are sitting in a warehouse. You go and you randomly sample 5 batteries, and then you drain them under conditions that mimic normal use. All right, so here are the lifetimes in hours of the 5 batteries. So we have 5 batteries, and we did this to the nearest hundredth of an hour, and so here they're listed here. All right, so what we would want to do is say, okay, so does this sample of 5 batteries support the engineer's claim that the batteries will last on average 17 hours? So the first thing we might do is calculate the sample mean. So put that data, you might pause this video and put this data into list 1 and do a 1-var stat in your calculator and calculate the mean. All right, so I got a mean of 16.29 hours. Assuming I did that correctly, and let's assume for right now that I did. And so we had 16.29 hours is the sample mean, the X bar. So is that, it's certainly lower than the 17 hours. It would have been great if we had gotten very close to 17, but we're a little bit low. But we're still within 1 standard deviation of the hypothesized, or the mean that the engineers think should happen, is 17 hours. So how likely are we to have a population that really is 17 hours on average, but that our sample is only 16.29? That's the whole point of this discussion is, we will sample from the population and we hope that that sample will be representative of the population, but samples always vary. So we would have to figure out, how likely are we to get a sample mean as low as 16.29 if the true population mean is truly 17 hours, right? And then, of course, the sample size is rather small. Well, we might graph that data. So that's what we're asking you to do, is put those on a histogram, as you see here. So we could add those to a histogram. Go ahead and do that. Shade in each block for each one. Careful, the class widths are 0.25. So this is what I got when I plotted those 5 data values. So they do appear visually. You can see that 4 of the 5 are below 17. We have one that's above 17.5, so that's good. But is this representative, right? So the sample's kind of small. So what we might want to do is take a sample more. So if we did 15 more batteries, so now we have a sample size of 20, we randomly selected 15 more. Put that data into your calculator, into list 1, add it to the 5. I have them grayed out here. Those are the original 5, and then there's 15 new ones. So add those 15 to your original 5 in list 1, and then calculate that mean. All right, so I got 16.57. So now we're talking, it's a little closer to 17, what the engineers think is 17 hours that they will last. But ours are still a little bit lower. So again, we want to think about how likely are we to get a sample of size 20 that has a mean of 16.57 when the true population mean is really 17, right? So if the engineers are right and we have 17, not every battery is going to last exactly 17 hours. Some will last a little longer, some will last a little less. We would not expect every single battery to last exactly 17 hours. There'll be some variability in each battery. But our sample is fairly low, so how likely? Again, that's what the whole point of this chapter is we're going to develop methods for figuring out how likely are we to get a value as extreme or more extreme than the one we got from our sample when the true population is really 17 hours. All right, so we might say we want to plot this data as well to get a visual. So add this 15 data values to our histogram. And I get something that looks like this. So again, the data doesn't seem to be centered on what the engineers think is the mean for theirs, right? So our sample distribution is fairly varied and not really centered on the 17. It seems a little lower than 17. But again, this is a sample. We don't know what the true population is. We're just using our sample to infer something about the population. All right, so we might think, well, let's take a larger sample. So in this slide here, I'm taking a sample of 50. Now, I'm not asking you to do the sample mean in this case. I just gave it to you. So the sample mean when we did 50, so we added, what, 30 more to our 20 to give us a total of 50 now. If we graph that, we get something that looks like this. And so you can see that this is starting to look kind of symmetrical. It will probably be bell-shaped if we took a large enough sample. Our sample is still 50. It's not that large of a sample. So we would not expect it to be a perfectly smooth normal curve, but we would expect this data to be fairly normal. And you can see it's fairly symmetrical. You can see where the peak is. You could probably say, well, the median is probably something around 15.6, something like that. I'm sorry, 16.6 or something like that. And we can see the mean is 16.68. So that's the measure of center that we're using here is X bar, but you could say kind of median would be right about in the middle. All right, so I listed here on this slide the 5 X bars, the 3 X bars. The one when we had a sample size of 5, then the one that we got when we had a sample size of 20, and then the X bar that we got when we had a sample size of 50. So which one of these would be the one we would use? Would we use the sample size of 5, the sample size of 20, or the sample size of 50? Kind of makes sense that we would use a sample size of 50. Again, of course, assuming that we are not violating our 10% rule, right? So we're a large battery manufacturer. You can assume that they made at least 500 of these batteries on the first day, probably. And so our 10% rule is satisfied, so we're okay with that. So probably the larger the sample, the better. Again, assuming that we're not going over 10%. So the 16.68 hours is probably the best one. All right. So the whole point of this chapter is to understand the difference between a sample and a population, and ultimately to calculate what's the probability that we would get a sample as extreme as we did. So in this case, how likely would we get a sample mean or X bar as low or lower than 16.68 when the true population mean is 17? Now, we don't know what the true population mean is. The manufacturer of the batteries doesn't know that either, unless they took all the batteries they produced and drained them all. Then they would know what the true population mean is. But they're not going to want to do that because then they won't have any batteries to sell. So they'll never really know what the true population mean is. And in reality, most times we don't. In this case, we are hoping that our X bar is representative of our population, right? Our X bar will be representative of our population mean, in which case we would say that the engineers probably missed their mark a little bit. The batteries do not seem to have a mean lifespan of 17 hours. They seem to be a little bit less than that. All right, so in this chapter, we're going to hopefully, if you have not begun to read chapter 7, you will, because this is going to be a very confusing topic, this sampling distribution. And hopefully by the time we're finished with 7.1, you'll get a good feeling for what that sampling distribution is. We're actually not going to talk about that today. We'll get more of that in next class. Today, really what we're going to concentrate on. We have a number of things we're going to do, but today we're really just going to talk about and distinguish between a parameter and a statistic. The rest of these things we'll do next class. All right, so statistical inference. So it's really the whole, one of the main concepts in statistics is inference. And so what do we do when we do inference? We have a population and we want to measure something about the population. If we're dealing with the batteries that we just talked about, we want to know how long the batteries will live, how long, their usefulness is. And so we want to know what the mean lifespan of the batteries in this new AAA battery population is. And so what we do is we take a sample and we measure something about that. We collect data from that sample, the lifespan of each battery in that sample. And then we take and we make an inference. We say something intelligent about the population based on that sample. So we will say that I believe our sample lifespan, average lifespan of the sample of batteries was 16.68 hours. So we would probably say, after that was for the sample of size 50, we would say our population would be estimated using that X bar. So that's the whole idea, is often we cannot measure something about a population because the population is too large. It would cost too much money, take too much time to measure the lifespan of every battery produced. And if we measured the lifespan of every battery produced, we would have no batteries to sell. So we're not going to look at the entire population. And usually it's because it's too expensive or takes too much time to do. And so we will take a sample. And that sample, we collect data, we measure the lifespan of the sample, and we get the average. And we, in turn, then say something intelligent. We think the lifespan of the new battery is 16.68, for example. All right, so this takes us to the idea of parameters versus statistics. So the parameter is just what we call the thing we measure about the population. So in our case, the population mean lifespan of the battery, that was a parameter, okay? The thing we measure about the sample, that is the statistic. So the X bar in our case, for the battery example, the X bar was the statistic. All right, we use Greek letters traditionally to denote a population. So a mu, looks like a U with a little tail on the left side, is pronounced mu, and that is the mean of the population. And usually we don't know that. Right? If we knew for sure how long the batteries lasted, then we wouldn't be taking a sample to try to estimate it. All right, X bar, which is just an X with a little line above it, and that's pronounced X bar. And in our case, if you need to type that out, you can just type X bar, X and then the word bar after it is fine. All right, and that is the sample mean, the mean of the sample. All right, and then sometimes we aren't interested in mean, but instead we're interested in proportions. So for example, I might want to know the proportion of Montclair voters who voted for Donald Trump. So I probably would never know the true proportion of voters in our population of Montclair voters who voted for Donald Trump. Probably never be able to truly know that. But we would use a lowercase p to represent. Now, I said Greek letters, so some places use Greek letter pi to represent the population proportion. So if we are trying to estimate the true proportion of Montclair voters that voted for Donald Trump, we would probably not be able to measure that, but instead we take a sample and ask the voters in our sample, randomly selected, did you vote for Donald Trump? And the proportion in our sample would be denoted as p hat. So it's got a p with a little caret above it, is denoted as p hat. And you could certainly write out the p and then the word hat after it, because we have a hard time typing p caret with a caret above it. So p hat would be perfectly fine if you're trying to write that or type it. P hat would be acceptable. So p hat is the sample proportion. So in our sample, the proportion of people that voted for Donald Trump, and then that would hopefully be used to estimate the true proportion p. And again, some textbooks, and if you use internet websites, sometimes they might use pi to represent that. Okay. All right, so we use the x bar to estimate the mu. So we use the sample mean to estimate the population mean. And then we use p hat, the sample proportion, to estimate p, the population proportion. All right, so in one way to sort of remember which one's which goes with which, a statistic starts with S, and it comes from a sample, which also starts with S. Parameters, which starts with P, they come from something measured from a population, which also starts with P. So the S's go together and the P's go together. All right, so here's some examples. And what we want to do is write what it is. Is it a statistic or is it a parameter? And then what symbol would we use to denote it? So for each one, write the appropriate notation next to it, and then also whether it's a parameter or statistic. So the first one, on Tuesday, the bottles of Arizona iced tea filled at a plant were supposed to contain an average of 20 ounces of iced tea. So when a machine is filling a bottle with liquids, in this case iced tea, it's not going to be exactly 20 ounces every time. Sometimes the machine overfills it a little or underfills it a little. Okay, so it's supposed to fill it with 20 ounces of iced tea. Quality control inspectors sample 50 bottles at random from that day's production. These bottles contain an average of 19.6 ounces of iced tea. Okay, so we have two numbers, that 20 and that 19.6, which is a statistic, which is a parameter. And what symbol? Are we using an X bar? Are we using a mu? Are we using p hat? Or are we using p? All right, so the 20 ounces is measured from the population, right? It's denoting what we think the population is. And that is a sample mean number of ounces. So that will be a mu. And then the 19.6, that's measured about a sample. And so that's our X bar. It's the mean amount. So we could use X bar if we wanted to denote that. You could type X bar if you want. Okay. Number two, on a Newark to Denver flight, 9% of the passengers were selected for a random security screening before boarding. According to the TSA, 12% of passengers at this airport are randomly chosen for screening. Okay, so the 9% and the 12%, which is a parameter, which is a statistic, and what symbols would we use for those? All right, so the parameter is P, is the 12%. And that's, you can think of that as the population of all passengers at the airport. And then we have a sample, one particular flight, and that's our sample. Maybe it wasn't randomly selected, maybe it was, who knows. And that is a statistic, that's the p hat, that's 9%. All right, so again, you could type that as p hat. The X bar, X with a bar above it, can be written as X bar. Okay, so your homework tonight is going to be just asking you to look at situations and then talk about those numbers, right? Which one is a parameter, which one is a statistic, and what symbols do we use for each one? Okay. And so that homework will be due next class, and that's it for today.